Good morning, good day, everyone. My name is Tony. I am a course advisor and I'll be your host for today's webinar. Just some housekeeping rules before we start. So on your screen, these are some notification and sound options. So you can turn on and off the notification as you see fit during this webinar. And please post any question under the Q&A function at the top right-hand corner. You'll see it there. That's where you can post any questions that you may have. There will be a Q&A session at the end of this webinar. So you can just post your questions there and it will be answered at the end of the webinar. Moving right along. So these are some of the common questions, frequently asked questions. Registered for this webinar will receive a copy of a will receive a hello. Yes, so everyone registered for this webinar will receive a copy of the PDF slide and a link to the video recording within the next 2 business days. So please do check your junk folder, spam folder, if the email does not appear in your inbox. And also we will provide you with a free digital certificate of attendance for the attendees. So you will get a QR code at the end of the webinar, and I'll also share a link to claim that certificate of attendance. So just stay with us until the end of the webinar to qualify for the certificate of attendance. Okay, so event conduct. So please keep discussion lawful and respectful. Follow the moderator's directions. Do not share illegal or abusive content. Recording is not permitted unless authorized. Breaches may lead to removal and referral under ECT policy. And today's topic is microgrids and the future of energy decentralization. And our presenter for the day will be Dr. Walid Issa, and he's our ECT program leader. Dr. Walid, you can take over.
Okay.
You can take control of the slides.
All right. Thank you very much for this introduction. And welcome, everybody. I hope the sound is clear and you can hear me. I think. Okay, so let's get started with this webinar. The title will be Microgrids and the Future of Energy Decentralization. My name is Walid Issa, and yeah, you hear me?
Doctor, just to interrupt you, Doctor, is it possible to take control of the slides?
Yeah.
Perfect. There we go. Right. That's great.
Thank you. Okay, welcome everybody again. So again, the title will be Microgrids and the Future of Energy Decentralization. My name is Walid Issa, Associate Professor in Power Electronics. My studies during my PhD for a long time about microgrids, about power electronics, converters and their integration, and how they facilitate the integration of renewable energy resources into the grid in terms of the topologies that we use and the control strategies that we propose. So the microgrid topic is a trend for maybe more than 15 years now, and the concept is to enable something called decentralization, and we will explain through the slides what we mean by decentralization. So next one. So when we talk about the electrical grid or the structure of electrical grid, I mean the traditional one. We know you have a power station. That power station exists somewhere in your country, for example, and it delivers that power through a series of transformers and transmission lines to step it up, step it down, for long distance until it reaches the facilities that they want to supply power to. For example, homes, institutions, hospitals, factories, or maybe residential consumers like homes in the other part of the country. So in this traditional system, we have power source, we have long transmission lines, we have losses through these transmission lines, and then we have the customers. So when you look at this traditional system, it's very easy to identify some weakness point in that system. Maybe we rely on huge power just generated at one point of the system. Any risk happened at that point, any problem happened at that point, you are uh, threatening the supply for the customers on the other part of the country, and also for a large part of the customers as well. Anything happen to the transmission line and storms, they also make an interruption for the service and reducing the quality of the service. So the problem with the traditional structure is the dependency on a high capacity fossil fuel, increasing the carbon emission, because most of these plants and power supply stations, they rely on carbon or coal and fossil fuel to generate the electricity. Getting a large amount of power in one place is also a risky. For example, if there is a conflict happen between two countries, maybe hitting one of the power plants, making the country all fill or live in dark. Using a long transmission line to deliver power that increases the losses and make it less economic, and finally has low reliability against sudden faults. If something happened to the transmission line transformers, you have some interruption of the service and lower quality delivered to the customers. So that's why the microgrid concept born, maybe more than 15 years ago, 20 years ago maybe, and some deployment recently happened. But the concept is, instead of relying on a central power plant, they are integrating something called distributed generators. Distributed generators means we have other sources of power, for example, solar power, wind power, maybe combined heat and power plants, fossil fuel on hydrogen, and they generate electricity within a region or a land, and they share their power with their customer there. And if they need more of that power, they can really take it out from the central power plant, or if there is some excess power there, they can even sell it to the grid. So this kind of structure, or microgrid, or mini grid sometimes, or a smart grid, they give it that name as well. This release some pressure. Okay, is there any problem before we continue?
They just are a breakage of I think of the voice. It just disappears a bit and comes back. So I'm not sure what could be the issue.
From my side.
But yes, from your side. But I can hear you now. I can hear you okay now.
Okay.
Yes. You can continue.
Let's continue. No problem. So this kind of structure enables the integration of more renewable energy sources into the system. They release some pressure onto the power plant. So if power plant has a problem, they still can supply each or themselves there, the customers, by the internal generation of the power of the renewable energy. And they can also facilitate the customers to be part of the network. The customer in the previous structure, the traditional structure, they can't really be part of the network. They are just consumers. But here, the customers are also producers, so they can sell power and they can interact. They can sell power at some point. They can consume power at another point, maybe midnight. So that kind of interaction will also make some value, additional value for the customers and for the other stakeholders. So in microgrid structures, we integrate more renewable energy. We control the flow of power. I, as a customer, I have solar power in my house. I can control if I want to sell that power to the grid, or I use it or store it in my batteries. and I can control the timing for that as well. So for example, I make charge of my batteries during the night time because it's less costly and the price is less. So that's why I can optimize my consumption and generation to make my bill as low as possible. I can control the power flow. I can reduce the carbon emission because I have solar power, and maybe the microgrid has other generation sources. We can reduce losses because the reliance on transmission line will be less and less, and the current in through this transmission line will be less because you already, as customer, you have some generation there, so you don't need to uh, um, deliver a lot of power, and this will minimize the losses as well. The last is reliable against sudden fault. If something happened to the generator or transmission line, you at least have some backup from your batteries, from your solar system in your microgrid. I don't mean a single customer, but as a community. And customer will be part of the grid. As I mentioned, they decide if they want to sell or consume. So that is the old traditional structure, which is centralized transmission line, a centralized power station, and power generation, to distributed power generation and what is called microgrid or smart grid. So what kind of microgrid modes we have? In this part here, to the right-hand side, we have some loads, which is the customer, factories, hospitals, maybe residential houses, and we have some other generators, maybe wind generators, solar generators, diesel generators for backup, or other generators as well. They can generate power, and we know that renewable energy generations can't be the main one because they are intermittent. We have solar power in the daytime, but not in the time. Um, and we have wind turbine, but wind energy, but it's not expectable and it's not constant. So we might have today some wind we generate, but tomorrow not. So that kind of intermittency makes a problem. So that's why they rely on other resources to be the main generators in case we lost the source. So this source is the grid. And what is the switch? The switch now controls if we want to be connected to the grid or disconnected from the grid. So that's the microgrid, and this is the grid, and this switch can make us in a grid connected mode or in something called island mode. If that switch is closed, conducting, that means we are in grid connected mode. If it's open, that means this part here is isolated or island mode. We call it island mode, or we call it isolated mode. And this bus here is called the point of common coupling. So about the interface, if, for example, we want to do to make a microgrid, we know that you have some solar panel, maybe renewable energy from tide, from wave, from wind, but each source of these things are intermittent. Each source is not fixed in terms of voltage and current in power, and we need some regulators after this. And we might use some converters, and these converters can be integrated to also enable some battery storage inside them. So we have sources, we have between here some converters. They store the energy in batteries, and then we use the battery energy into and convert it to AC, and we go to the inverter. Again, I see a lot of noise from the chat.
Oh yeah, they're just saying that there's an issue with the sound, or the sound is not clear, but it comes and goes basically then. But most time we can basically hear everything.
Slides are appearing to them.
The slides, well, they're saying that it's not visible. So what I'm assuming is that I've advised them to just refresh the page and join in again. Sometimes it might be that yes, there's just a
Yeah,
delay with their internet. So
no
I've
problem.
just advised them
I
to.
will continue because I can't really focus on both now. Okay, thank you. So
Yeah,
sorry for
some
interruption
some
because
they're
of
saying that
some
they can hear, so
technical.
you
Yeah,
can.
yeah, yeah. Sorry for interruption, guys, but there are some comments coming about the slides and about the sound, but it's kind of we are already doing it as usual, so we are not expecting any problems now. So again, we have sources, we have some converters, they dump the power into the batteries, and then we converted to the AC. Why we have to convert it to AC? Because the source here, most of these sources, not all of them, but most of them are DC sources. We can store it in batteries, which is DC source again. But when we want to supply customers or connect it to the grid, we have to convert it to AC. That's why we have here AC DC to AC converter, which is called inverter. And from the output of the inverter, we can supply our loads. If we have, for example, lamps, we have TVs, microwaves, fridges, or we can sell it to the grid. So that is maybe one of the shots about integrating solar energy. For example, we have the sun power can be generated by PV panels, and that go to converters to charge batteries, and then the battery use inverter to convert it to AC load. If you have DC loads, for example, you have some lamps, maybe you have a caravan and you have some lamps, you can really get the power out from the battery straight away. You don't need an inverter for this because the lamps are DC and the battery is DC. Now, the structure of the inverter, because going into microgrid, you have different levels. I'm just talking about people want to know about microgrid and maybe work in microgrids later. You might be not technical guy. You might be a top layer guy, which is policymaker, maybe energy management expertise. Okay, you don't need to know the technicality. Okay, but if you are a researcher, for example, or you joining power electronics industry, you have to know the technicality. Okay, so from the top layer, this slides will not be beneficial a lot for you because the policy will be different from one country to another country. The deployment strategy for each country is different, and the energy management as well, it's not a big issue because if you collect the data, it's kind of decision maker. Maybe SCADA system will work, and then you decide which part you want to close the switch, which part you want to sell power or import power or export power. All these decisions can be done on the top layer. But now we will go now down into the technicality or the component itself, which is the inverter. The inverter is the main component in microgrids. Because if you have solar, you have wind, you have fossil fuel, if you have batteries, they can't really integrate with the grid without inverters. So the inverter is essential part there. What is the inverter from inside? It's two-leg or three-leg switches. We call these power switches, and what is here is IGBTs. These IGBTs or MOSFETs, they convert by signaling. You pulse them by something called PWM or pulse width modulation, and you have battery here. That battery will supply the left side, and then using the switches, they can generate something called modulated sine wave. Modulated sine wave, it will appear here, and it will be filtered from the high frequency components, and pure 50 hertz sine wave will appear here, which is exactly matching the sine wave that you also receive from your grid supply. So this now kind of structure will enable also the integration from other sources exactly to the grid. Now, when we look at the inverters topology, there are maybe a few topologies in the literature. One of them, for example, if you have BV or you have battery system, which is DC system, you can convert it to another DC level. So this one is called boost converter. So for example, I have battery which is 200 watt, but my inverter to generate AC power here, it needs at least here 700 volt. So I have 200 volt. I want to push it up, step it up to 700 to make it suitable for my inverter to convert it to AC. My inverter can't take the 200 volt. Maybe that's the range of operating point. Okay, so that's why I have to make a step up voltage and make it 800. So this one is 200 volt DC to 800 volt DC, and then we can convert it to AC. So this is one of the structure. Another structure is you have DC, which is low voltage, maybe 200 volt, and you convert it to equivalent AC source, okay, which is inverter here. But if you want to step it up, for example, to 300 volt or 200 volt to 20, okay, or 230 volt, you have to use a transformer. And this kind of structure, we use big bulk transformer because the frequency out here is low frequency. So this one is an old traditional example of an inverter and can't be used for very high power example or structure or loads, because the transformer here will be big and also the DC converter will also be big and bulky, and the efficiency will be less. The next one here is called this DC converter with a transformer, but not like this one. This one is stepping up or down the low frequency, which is 50 hertz. But here we have 200 volt, for example, and you step it up to 800 volt, but using very high frequency pulsating. That very high frequency pulsating makes the transformer size like your hand. It's not bulky, for example, like a room, okay? So this one will be the size of your hand, for example, to convert 200 to maybe 700 volt, and then you convert it to AC by inverter. So this one is low frequency transformer. This one is high frequency transformer. Another one is, no, you don't have low voltage. You have 800 volt already there, or 700 volt by stacking more series panels or batteries, and you can convert it straight away or use it as it is from DC to AC. Okay, so these are some examples of how the inverter really integrates sources into the grid. So this one using boost converter, this one transformer, this one also transformer to step up DC to DC. So this one is DC to DC, but this one is AC to AC. And the last one is using many PV to step up the voltage and convert it. So about the controller, now we have here a grid and we have our inverter, and the main thing that we want our inverter to generate AC that matches the grid, and then we send the power to the grid. But how we control how much we want the power to go out or to be fixed or regulated at some point, we have to measure the current, we have to measure the voltage, and by some controllers, maybe resonant controller, PI controller, we have plenty of controllers. They can regulate the amount of power that can be exported. And at the same time, if you have a battery here and you want to import power from the grid during the night time, also this can be managed by a controller. You can't just make an inverter that generates sine wave and just connect it to the grid, because this will be very risky. You have to have synchronization and you have to have something called controller. Maybe droop control can be one of them as well. And these are some values and some examples of the controllers and values that they use and sensors types. This is just for the people that they like technical parts and they want maybe, or they are already engaged in research and they want to know what kind of sensors there and what kind of controllers they can use for this example. When you look at the electric vehicle, okay, what we describe in microgrid is exactly, electric vehicle is a small example of that. So in electric vehicle, we have battery. That battery might be enough to be used for the inverter, or we need to boost it up. So that's why the battery here might be 200 volt or 400 volt, but we use boost converter to convert it to higher level for the inverter, and that inverter now controls what? Controls the electric motor or machine that drives the wheels. At the same time, you can take some of that DC power to supply some auxiliary units, for example, your lamps and your wipe motors, or maybe your radio or other things. At the same time, you have battery charger here. That battery charger will take power from AC supply here and convert it to DC and control the power with protection as well to charge the battery. So again, we have a lot of power electronics stuff there as well that also has the same structure as the inverter and has some sensors and feedback, and maybe use the same controller board and to control what? Control the voltage level, to step it up, and maybe the form to convert it from DC to AC, and then go to the final destination, which is a motor in this case. So there are some like similarities between the structure of the electric vehicle and the structure of a unit in microgrid as well. To control the power that comes from your house, for example, or your maybe a solar farm or battery system, and you want to control the active power and reactive power that you sell to the grid, you have to have a way to measure the active power and reactive power. How do you do that? They do that by measuring the voltage and current, the instantaneous, not the RMS value or average value. The instantaneous voltage and the instantaneous current, they multiply them, and then they filter. So they produce the output here, and they pass it through a filter, low pass filter, and after this we can get something called the active power P. If you want to measure the reactive power, you make a shift by 90 degrees for the voltage, and then you multiply it by the current, and then you pass it through a filter, and this is why, or this is how you get the Q. So why we measure the power and reactive power and active power? That help us, for example, or help the inverter to decide if they want to contribute to power factor correction, or they want to contribute to sell more power to reduce your bill. And it depends on the size. For example, if we talk about a few inverters and they are stacked beside each other, and they all together, for example, contribute by 1 megawatt, for example, or 1 megawatt hour, 1 mega VA. So that means they can contribute by power, or they can contribute by reactive power. So they can help the microgrid to achieve higher power factor. Maybe they can achieve also or contribute to the power regulation and voltage regulation. You know, when you have a bus and your solar system is generating more power into that bus, your voltage will be rising. And if your voltage rising, the TVs and microwaves in microgrid will shut off or maybe damaged, okay? And some of the instruments will stop. And you have to decrease it. That the regulation of that power and that voltage, that can be done by exporting and importing more reactive power. So if you export, you can rise. If you import, you can decrease, and if you export, you can rise the voltage. And based on the amount of Q you push and you take into that bus, you can contribute to the regulation of that voltage. For the power, it helps to regulate the frequency if you are in isolated mode, and helps also supply our customers. And about the technicality again, we have inverter and we have switches, and what you see here is kind of an example of how the sine wave, how the inverters generate sine wave. They have sine wave as reference here, and then they generate something called PWM to the switches. This PWM is a high frequency pulsation on and off, but high frequency, but they modulate a sine wave. So after I pass that signal out into through a low pass filter, which is the LCL filter that we showed in previous slides, that means a pure sine wave will come out. This kind of technique minimizes the size of the filter, minimizes the size of the inverter as well, and make it more robust control, because we can generate any sine wave with any frequency, with any amplitude as well, very fast. So if you want to go through a research into microgrid and see, okay, what are the challenges and what are the proposed solutions and what are the goals of each part in the microgrid. For example, one of the main objectives in microgrid is the voltage and current regulation. And the goal, I want my inverter to produce low distortion sine wave. I don't want it to be with harmonics, because harmonics makes a problem. So I want to make my inverter to produce a pure sine wave. How to do that? With no resonance. How to do that with regulated voltage? How to do that with smooth step response as well? We can use PPI control, resonant control, adaptive control, repetitive control. So for example, because the target of this webinar is some people, they want to know about microgrid concept, but also it targets some people, they want to study microgrids as well. And maybe they are PhD students somewhere and they want to contribute to that. So you can use one of these controllers to achieve this goal. Another goal is power sharing. For example, if I have an inverter in my house, my neighbor has also an inverter in their house, and also other inverters in a community. We have hundreds of inverters. How we make sure that, for example, if the microgrid is a setup that want to achieve that goal, how we make sure that we can control the power output and power sharing between all these inverters. So the goal is adequate power sharing. Adequate means if I have inverter which has higher capacity, I should export more power, for example, than my neighbor. So how we achieve this kind of control, accurate power control. If I want, for example, to export 1 kilowatt, how exactly I can achieve that? What kind of controller I can use? Without communication, that's a key. I don't want to use communication between me and the central, between me and the other members of the community, or maybe microgrid, to achieve that power control. What kind of solution we have? And we want also very good step response for this. So the solution is, you might use some master-slave controller. One will be master and the other is slave, and we have central unit to conduct or command other inverters to do to follow some set points of the power. Or maybe you have something called current chain scheme. But the most maybe popular one, which doesn't need any communication, is called the droop control. Droop control doesn't need any communication. It relies on the frequency of the bus. If the frequency of the bus is lower, they push more power. If it's higher, they push less power. Okay? And if it's above some limit, they export even power. So the frequency of the bus is kind of communication signal between the inverters, but without communicating between themselves. Okay, we don't need any communication module. So the droop control is very, very popular and also a robust one, and that enables something called hot swap plug-in inverters. So you don't need to communicate with others. You can just turn on your breaker, and that's it. You don't need to communicate at all. Now, power sharing, again, the droop control, how droop control works, and what is the advantage of droop control? It can generate accurate power control, but unfortunately, it can generate active power control, but not reactive power control. So one of the goals is how to change that droop control to make it accurate in reactive power as well. Reactive power can be anything, so that's the problem. We need small frequency and voltage deviation. Again, when you push power into the grid or into the bus, that frequency will deviate up or down. That deviation, for example, in island mode, we talk about island mode, that deviation has to be restored somewhere. And also harmonic sharing. For example, if we have customers, unfortunately, they use equipments that they generate harmonics. How we make the inverters as well also share the harmonics. We can't make one inverter produce harmonics that maybe stress the components and makes a problem. We want to share also the harmonics, not just the power. At the same time, we need also smooth step response. So how we can achieve these goals by PID control, by angle control, and by external supplementary loop. By the way, what I propose here is something that's in the literature. So I'm just giving you a light about what is in the literature and what has been published before and what has been produced before to achieve these goals. And for islanding, now I think some of you may be aware about what we mean by islanding detection. For example, if you have an inverter in your house, you have an inverter and you have solar power, you send that power to the grid. But what if the grid is absent? What if the grid has a problem and they disconnected that breaker, or the transformer in the way between you and the grid has been blown up, or the fuses has been blown up? What will happen to your inverter? Will it keep supplying that power to the transmission line and making a risk on any people or maintenance worker want to make any work on that line, or it will seize the power and stop it? This is called islanding detection. Now, if the islanding means the grid is absent for some reason, detection, we need to detect if the grid is absent. So now, if the grid is absent, we should have, our inverter should have some technology there to discover the absence of the grid without communication. Again, we don't need to communicate with the grid, oh, you are absent. No, we want to discover the absence of the grid within 2 seconds. Based on what? Based on IEEE standard. IEEE standard says you have inverter, it should discover the absence of the grid without communication within 2 seconds. So if this happens, if the grid is absent, the inverter should take action to stop exporting power to the transmission line to make it safe, and maybe it has a technique to isolate itself and still supply the house. Okay, so that's called islanding detection. And there are some passive methods and active methods, a lot of methods in the literature, and one of them is the inverter keep perturbing the frequency. Perturbing means the frequency of the bus. Now, if the grid is not absent, if it's present there, the grid bus frequency will be 50 hertz every time, all the time. So that means if the inverter tries to perturb it, it will not move. But if the grid is absent, and the inverter now tried to perturb the frequency, for example, from 50 hertz to 50.1 hertz, 50.2 hertz, that means it's absent. So the perturbation is happening every second. And if the perturbation was successful, and yes, it's moving, that means the grid is absent and we have to take action. So now about the top layer. I mentioned some of the people, they might work on power electronics industries. They want to know how the inverter maybe look like, what kind of controls there. We explain that, and what problems. But also we have people that work on top layer, energy management, or demand side management, and these things. The controller is distributed into 3 categories. The primary controller, which is the control of the inverter power. Secondary controller, about the microgrid restoration, and also territory power control, which is the energy management. How much we need to generate, is it grid connected or no? Is there any battery there to charge it now or no? How many customers we have and how much load we have? All this kind of like discussions and making decisions will happening on that level. So that's the microgrid levels of actions here. About if you are working with research, and one of my researchers, I will talk about myself. I worked on paralleling inverters in island mode. How I make sure there is no circulating current. How I make sure that power sharing in island mode is adequate. How I will make sure that the smooth transition. For example, if I am in grid connected mode, and I want to move to island mode, or island mode and then want to move to a grid connected mode, how smooth? Because sometimes when you close that switch, a lot of inrush current might happen and damage the system. So that's why this kind of thing, I want to make sure that it's happening smoothly, and also to ensure that the stability of the microgrid. We don't want to, for example, to go to island mode and we lose the control because we don't have the ability to control the power from, for example, PV and battery. We have to make sure that everything is controlled very well. So this is the system that was under my study, for example, a grid distributed unit here, and another distributed unit here. That's a battery system here, and that's a grid system here. And I developed some controllers measuring by sensors, voltage and current, and measuring the power as I explained before, and commanding using group control the power from each unit. So the methodology that I taken, I want to make some microgrid modeling, which is more mathematical maybe work. I need to propose a controller and use MATLAB and Simulink, and then implement it practically. So this is kind of inverter that I built in my PhD about some semicron here inverters, LCL filter, yes, bulky, but you can use lower one. We have some sensors here, and we have power supplies for the sensors. And finally, we have the interface and controllers here. I used for this kind of system, I use DSpace. So this is just shedding some light on some controllers. And what I describe now is something that happens in the research and developing centers. So microgrid concept doesn't appear mature to the industry in one night. It takes decades of research and development in companies, in universities, and this is just an example of what's happening there. So I used to develop some controllers for microgrid systems using DSpace system. They are a rapid prototype systems that can make, you don't need to code it, you just use MATLAB to program it. And there are some loads and the inverter here, and the GUI is showing every quantity you have: power, instantaneous voltage, instantaneous current, reactive power, and active power. You can control it using that system. And yes, based on the contribution that I have and the controls I developed at that time, I was getting 1.8% harmonic distortion, which is lower than 5%. That's success. So my inverter was working very well and producing a purely sine wave, and that can be now injected to the grid. And when I inject it to the grid, or I have two inverters, they want to integrate between each other. So this is what's happening. For example, that's the inverter reactive power number 1, and that's the inverter 2 reactive power. They are not similar to each other, and we have to make them similar. Why? Because we want exact reactive power sharing. So I have developed a controller. That controller, this is before enabling the controller, and this is after enabling the controller. We achieved kind of equal power sharing between them. So about other maybe parts of the research, maybe you can explore. For example, if you write my name, Walid Issa thesis, in Google, you can find it and download it. It will explain more about technical part and the controls that I developed, and also the modeling that I produced. Okay, and the published paper as well. So in terms of the takeouts from these slides, I think we have shed some light on to the importance of microgrids and how the microgrids will enable two things, main and new things, which is the integration of more renewable energy and make the customer part of the network. I'm not a passive element. I'm not just a receiver. I am a receiver and sender as well. I can control my consumption. I can control my profit. Even you can make a profit. I remember my last month, because I have solar system, my last month was good sun, to be honest, and I didn't pay my electricity bill. It came in negative. That means they should pay me, okay? Because I produced power more than what I consumed, okay? And that makes not bad payback. I shed some light into the voltage current controllers, reactive power control problems, what is the meaning of islanding, and the supervisory control, a little bit, not too much. And if you want to explore more, I want you to search on something called maximum power point tracking for solar systems. So maximum power point tracking, I think most of the solar systems in our houses now, they have a unit there inside the inverter. Is called maximum power point tracking, which is extracting the maximum power of your solar panel and converted it to AC, and maybe before converting it to DC to AC, they store it in batteries. So I think at the end of the slides, or the concept is, they developed this microgrid system. We as researchers develop controllers, developed strategies to enable the customers and to produce this concept to be more mature, to be commercialized, and to enable the customers to be part of the network, to achieve more optimized power consumption, and to also contribute to make less carbon emissions. Because if we use more solar energy, for example, and wind energy, we don't want more energy from the central power unit. That means less synchronous generators can be used there and less carbon emission can be released. That's the main goal that I think every country now tried to achieve. And I think I finished my slides. If you have any question, please drop them in the chat room or Q&A section, and I'm happy to answer if I know the answer for this. Thank you very much.
Thank you very much. Thank you very much, Dr. Walid. I think that was very insightful, and it was simplified actually. I think hopefully also the attendees got to learn a few things. And I would like to thank all the attendees for taking their time to attend. And just moving forward, on your screen, these are some of our upcoming courses. As you can see on the right-hand side, those are the start dates. But for more information, you can visit our website and we'll be able to assist you regarding anything that you might need. And on your screen, this is a QR code. This is the certificate of attendance. You can just put your phone on this QR code to claim your certificate, but you will get an email in the next coming 2 days, 2 working days, for the recording of this session. So let me see if we have any questions. So we don't have any questions. So I'll take that all the attendees understood. I think, as I've said, that I think it was simplified by Dr. Ali. So it was simplified. It was insightful. So let me just put this here on the screen. So these are our contact details. So you can visit our website. Our course advisor will then reach out to you then if there is anything that you want assistance with. Doctor, any questions? They are just grateful for the presentation. Any last words from you, Doctor?
No, I think thank you very much. We also encourage all attendees to, maybe if you are new to this sector, it's good to just make a Google search on this topic. It depends on what you really want, what's your ambition. It's also good to mention that we are welcoming PhD students, MSc students, and maybe you might have a chance to work on micro systems as well. Yes, that's it. Thank you.
Okay, that's great. So I'm going to share the link now for the certificate of attendance. Just now on the chat box, I'm sharing it now. So you can click on the link to claim your certificate of attendance, and it will be sent to you. I think we are at the end of our webinar because we don't have much questions from attendees. And I think everything has been covered. Once more, I would like to thank all the attendees took their time to attend this webinar. And obviously, then I would like to mostly thank Dr. Walid for this wonderful presentation, insightful, and I think, as I've said, simplified version of what was discussed today.
Thank you.
So I think we're going to call it a day. Anything from your side, Doctor? Everything has been covered? You okay? Perfect. So thank you, everyone. See you on the next one. Bye-bye for now.